And my slides are perfect. All right, so good afternoon, everyone. My name is Charles. I'm a PhD candidate at McGill University. I do this project with Bruno Tremblay and Robert Newton as well. This project is a contribution to the FRAMS project, which is itself a MIOPAR-funded project that is also a YOP-endorsed project. So improving the optimal interpolation scheme for a seamless CI motion dataset. Yeah, before going into the CI motion talk, I want to just give a little bit of context and motivation on how does this relate to polar predictability. So you have a picture here of a nice occurrence of wind-driven coastal polynyas of the Eurasian coastlines. And yeah, like why are we interested in such a dynamical feature or mechanism? In previous research, we have developed a method to quantify the integrated area of coastal divergence through winter. So we were seeding tracers in the sea and calculating sea ice trajectories by forcing it with observational sea ice motion vectors. And what we found is there is a strong correlation, we find a good correlation between late winter coastal divergence and the following September minimum sea ice extent at regional scale. And this mechanism is occurring as you have opening of coastal polynyas in the winter. This open water refreezes, but it's thinner ice than the ice that was present. So this dynamic mechanism preconditions the ice pack for the summer melt. Yeah, so here's the link with predictability. So it was a very interesting study that we based off the sea ice motion data set from the NSIDC, which is called the Polar Pathfinder dataset. The way it works, it combines drifting buoy data, satellite-derived drifts, and free drift estimates together to provide, which is one of the key features of the Polar Pathfinder dataset, a spatially and temporally complete dataset for sea ice motion. But to say the least, there are rough edges in this dataset, and this is what we try to address. One way to understand the challenges in producing these or combining these different ice motion data sets, here what you see is a seasonal cycle of the availability of satellite-derived drift data expressed on the y-axis as a percentage of the ice extent where you have the satellite-derived drift data available. And you see that it's pretty good in the winter, but in the summer you have this quite important gap due to the retrieval methods that kind of fail when the ice surface gets wet. And therefore, like an exercise such as the Polar Pathfinder blended dataset has to make an assumption or fill the blank, which can be done with free drift estimates of sea ice motion, but as you'll see later, the free drift estimates used by the NSIDC are notably slow speed, have a very important slow speed bias. So these are some of the things that we addressed. So aiming to improve these merged sea ice motion dataset, we defined two tasks. Task one, calibrate the different inputs that go into the construction of these datasets, and task two, improve the optimal interpolation scheme itself. So jumping straight into the calibration of the drift data input, the first project that I did was looked into developing better free drift estimates. So we work off this classical linear approximation to free drift. We have a linear relationship between the wind speed and the ice speed mediated by a wind ice transfer coefficient. And what you see on the map, on the left map, shows based on Era 5 wind data and the IABP drifting buoys, you see a spatial distribution of this wind-ice transfer coefficient. And we put this side to side with a map of the climatology of the ice thickness and biomass. So beyond the resemblance in the spatial distribution, we can also put them in relationship one to another. And you see that there is a first-order linear relationship between the wind-ice transfer coefficient and the ice thickness. And this is what we feed back into this calculation of free drift data input. And doing so we developed the state-dependent parameterization for free drift. And doing so, if we look at the seasonal cycle of drift speed, the solid black line is that of the drifting buoys, our reference. The gray line at the bottom is that of the free drift that was included in the Polar Pathfinder dataset, so the free drift from the NSIDC. And when we use our state-dependent parameterization to calculate the seasonal cycle of ice drift, we get this solid blue line. So we see that we correct for have an important correction for biases, and do a better job at representing the seasonal cycle. It's not perfect. It's a free drift, like first order estimate of ice motion, but it's still much better for the intended purpose of feeding it when we're missing other types of ice drift observations. So moving on with the calibration of the satellite drift input data, the plot at the top shows for the SSMIS instrument, if we look at different bins of satellite-derived drift speed, we get different mean bias errors, and we get this nice relationship between the two. So the error as a function of the satellite drift speed. So we use this to build a calibration function that we then pass onto the satellite drift data input. And yeah, it's about it's a small improvement, but it's about the 10% improvement on the satellite drift speed when we compare it to drifting buoy again. You see the two PDFs. The blue one is for uncalibrated drift. The red one is for after the correction. So mostly it goes and nudges a little bit of the error on the high speed biases for the satellite drift. And then, yeah, so I think we're going into task 2 now. So some of the things we did to improve the optimal interpolation scheme. So if you want to make an estimate at a specific location, you can look at all the points synchronous in time and associate weights to them. And a thing we've done is to implement a parameterization, error-based weights in our optimal interpolation scheme. Whereas the Polar Pathfinder was defining different constants that were associated to each of the input, constant for buoy, for satellite, for free drift, we changed that. We replaced that by a decaying exponential that depends on the error, on error maps for each of the drift sources. For the buoys, it's 0, this is our truth. But then you see those two maps, those maps of the RMS error for free drift and for satellite, that help define these, have a better resolution or better definition of these weights for the interpolation then. And what's interesting is you see that both the free drift and satellite, they are our calibrated input drifts, right? And they have a similar distribution of the error and magnitude. So what it effectively does, whereas the Polar Pathfinder was weighting the satellite drift twice as high as the free drift, we kind of even them out. So they have almost equal contribution at the end in the optimal interpolation data set. Yeah. And another small thing we did. So in the end, how we calculate one estimate, it's a weighted average of the available observations synchronous in time with their given weights. And we find that just a sensitivity experiment, by having a filter on the number of highest weighted points, we can maximize the error reduction and so on. So this is a little thing. The empirical value that we find is 4. So it means it's still better to do this a little bit of spatial interpolation, contrarily to having just the local estimate be your solution. But you don't want to go too far to degrade some features that you would have in your motion field. Yeah. So moving on, I have two more slides about some results. There's a challenge with validation. We would like to validate against the buoy data, but it's the data that we use to construct the data set. So a work around this, we randomly take out 20% of the drift data from the IABP data set. So we have a validation subset, and we use the remaining 80% in the construction of the merged sea ice drift vectors. I don't want to go into the details and the numbers here, but I included this table just to say that if we look, each line is one configuration of the optimal interpolation scheme. Each of the implementation that we do in itself improves the error metrics. And when we combine them all, they work synergistically to create our optimal interpolation solution. A visual way to look at it, if we look at scatter plots of the merged vectors, merged ice motion vectors against the validation, on the left side, you see what you get from using the Polar Pathfinder or original method. And the plot in the middle is the one with our new method for optimal interpolation. So you see that we fit much better, or we have a much better fit with the IABP validation subset. Similar story with the PDFs of the error. We both correct for for the mean bias error, so we center the error distribution and narrow it as well. Coming back to a plot of the seasonal cycle, the black curve, again, is our drifting buoy validation subset, so you get the seasonality. The blue curve is what you retrieve from using the original polar pathfinder optimal interpolation scheme, and the orange one is our new implementation of the optimal interpolation. So we, again, correct for biases that were there in the data set and have a better representation of the seasonal cycle. Yeah. And especially in the summer, so like, if you have in mind this like data gap in the summer that I was showing from the satellite data, it's kind of neat to see that we managed to address like these temporal gaps in the data set as well. And I think that, yeah, that's the last figure I have, is just to say that even though our like spatially averaged mean bias error is very close to 0, there are still some structures in the error. We tend to overestimate a little bit the velocity in regions where the climatology of the drift is slow, like north of the Canadian archipelago. And we still underestimate the velocity a little bit in regions of fast drifting ice, like the southern branch of the Beaufort Gyre or the Frem Strait. Yep, so that's what I had, just some words on the ongoing and future work. I'm looking into evaluating the continuity or seamlessness of the data set. We don't want to be introducing like discontinuities in those in the motion fields. To make full use of the IABP drifting data record, we're also looking if we can transition the validation step to high-resolution satellite imagery, for instance, like drift vectors from our GPS. And yeah, the last thing is also to extend the satellite drift calibration I did to the other instruments to cover the entire observational period, because at the end our objective is really to produce a readily available, optimally interpolated drift data set for the entire observational period. So I'll stop here. Thank you for listening. I'd be happy to take questions or talk about this after the session. Thank you.
Thank you, Charles. We have some questions here.
So with the 80% validation and 80% training, 20% validation, isn't one of the normal tricks you do with that is to then take another 20%, 80% and retrain and see if you get the same answer?
Sure, yeah. We did one implementation of it, but we could check for consistency. And I did check though that there was an even like distribution of the buoy point, that they're not, the 20 and 80% are not clustered in one place or the other. So it looks pretty like randomly spaced out, but yeah, sure, that would be a good extra validation, yeah.
Hey Charles, great talk. Maybe I missed this, but is this product available for people to go download and use?
Not yet, but yes, it will be. Like for instance, the free drift estimates are available already. Still a few things to figure out, but ideally by the end of next winter, it should be available, yeah.
Thanks.
Yeah. But that's the objective, have something that's available to download by the community, yeah.
I was curious about your use of the IABP data. Did you do any kind of filtering or quality control on it, like to remove tidal or inertial oscillations, or did you just use it straight up?
I actually used the drift vectors from the IABP process by the NSIDC, so they do themselves a little bit of that quality control, like they remove any drift that are beyond like 50 centimeter per second and velocity and so on. With respect to like tidal motion and stuff like that, I'm not exactly sure. But also the way they process them, they look at the noon to noon and midnight to midnight positions, and they do an average of these two. So it's a pretty straightforward way of computing the drift from the IABP positions.
And it would act to filter it a bit as well, I think, yeah.
Yeah, a little bit, yeah.
Okay, thanks.
I also restrain, like, only use the drift data within the Arctic basin. So, like, I also do a spatial filtering. I remove everything that's, like, in the Hudson Bay and the Canadian archipelago. I really focused on the Arctic basin. That was, yeah.